Hello everyone, welcome back to another discussion in dynamics. Today we will continue work energy methods. And plan for today is following. We will do a brief lecture review and then we will just focus on two examples. Example number 1 and example number 2. That's the plan for today. So without further ado, let's dive straight into our discussion. And our brief lecture review will take approximately between 3 and 4 seconds. Okay, because I think that actually I can summarize the entire lecture within these 2 sentences. Oops, not these ones, but these ones. So I just would like to remind you that work of internal forces is 0 when our bodies do not move relatively to one another. Okay. So, for example, if we have 2 bodies and they don't slide on each other, the work of internal forces between them is 0. So, if there is even if there is a friction between them, the work of that friction will be 0. And the same story with cables. So, basically, if we have 2 bodies connected with a cable, the internal force will be tension in the cable, but work of that tension will be 0 because the cable is inextensible. Okay, so just keep that in mind. And on the other hand, if our objects do move relative to each other, then the internal force between them does the job. Okay, it does the work. Yeah. So, for example, if you have 2 bodies sliding on each other, and you have friction between them, that friction will do the work. Okay, that friction will dissipate the energy in the system. Okay, sounds like a lecture review. Any questions about it? I don't see any, so what? So would you like to do example number 1? Let's do it. Okay. Let's do example number 1. As usually, please read and understand the problem statement before we start our solution. Alrighty, so what do we have in here? We have our body, we have one body in the system, right? Our body starts its motion from configuration 1, where it is placed here on the incline. Our incline has theta of 45 degrees, and our body has mass m. What else? We know that there is a friction between the incline and our body. And we also know that our body is distant by distance L from this, I don't know even how to call it, like a checkpoint, I know. Okay, anyway, this distance is L, okay? This distance is L. And what else do we have in the system? We have a spring. That spring has a spring constant K, and we know that at the beginning we have a preload present in the spring. So our spring is pre-compressed at the beginning. And they ask us to find what happens at configuration 2. So at configuration 2, our body has velocity final 0. And this is due to the fact that we compressed our spring even further by value S max. Okay, so basically we must find what S max is. Yeah, and maybe one more information. Our body also starts from rest. Yes, so our velocity 0 is also 0. Okay, any questions about the problem statement? I think everything is clear, yeah? So let's just dive straight into the solution. So this is my solution. And I will basically write down this expression. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And our job is to find these 5 expressions, or expressions for these 5 quantities. T1, V1, U12 non-conservative, T2, what I'm talking about, T1, V1, T2, V2, u-12 non-conservative. I like this order. Okay, so I'm going to go for the easy things, okay? I think that at the beginning our body is not moving, and at the end our body is not moving. So 0 here and 0 here. Kinetic energy at the beginning and at the end is 0. Okay, how about potential energy? Let's focus on the potential energy at configuration 1. Okay, so I think that in here we will have two contributors to our potential energy, right? First one will be gravity, and the other one will be spring, right? So we can actually split our V1 into V1 grav. It will tell us what is the potential energy coming from the gravity, and we can also have here V1 spring. Okay, what is V1 grav? It's mg times elevation, right? But before figuring out the elevation of our body, I must introduce datum in our picture, right? So I would like to place my datum here. This will be my datum. I think that VF is in my way, right? I will move it somewhere. I want to move you here. So this will be our datum. Okay, so it seems to me that elevation of our body is this distance, right? And I know that this distance is L. So this is L. So that means that that red distance will be L sine theta? I believe so. L sine theta. Great. mgL sine theta. Okay, how about spring? Our spring is pre-compressed, so this is the energy accumulated in the spring. 1/2 K delta squared. Okay, I think 60% of the problem done. Yeah, we found these three expressions. Cool. Now let's focus on potential energy at the end. And in here, again, we have two contributors. We will have V2 gravity plus V2 spring. Okay, so what is the elevation of the body in the end? Aha, I must figure out what is this distance, I believe. What is this distance? Here and here. I believe that analogically to the previous one, this distance will be S max sine theta. I believe so. This will be S max sine theta. And it will be negative, yeah, because our body is below the datum. So this will be minus mg S max sine theta. How about spring? Oh, our spring is even more compressed than it was before, right? So we have more energy accumulated in the spring. So in here I will have to write 1/2 K bracket delta plus S max squared. Okay, guys, I think that 80% of the problem is done, and this is a good time for questions. Do you have any questions? Would you like to ask any question? Yes, Olivia? Sure, because this is the distance we compressed our spring. Please observe that at the beginning, we had a preload delta. Yeah, so our spring is preloaded by distance delta. And in here, we compressed it even further by S max. So the actual compression in the spring is delta plus S max. Yeah, Olivia, you don't seem like convinced. Was this clear? Yeah. Okay, sorry. From my perspective, it looked like I confused you a little bit. Yeah, sorry. Yeah. Yes, Nathan?
Why is it negative mgs max?
Sure, because this is our datum. So that you see that red horizontal line is our datum, right? And please follow this point, so you can see that. Please follow that center point, this point. Maybe I will use blue one. Oh, sorry, that was eraser. This is. Oh. Why you're not listening to me? Yeah, so I am following this. I take care of elevation of that blue point. Do you see? Yeah. So this blue point is here. This blue point is below our red horizontal line. Do you see that, Nathan? So since it's below, the potential energy due to gravity will be negative. You also don't seem convinced.
Yeah, I'm convinced.
Okay.
Could you put the datum below if you wanted?
Anywhere you want. Yeah. I just put there. Yeah. Yeah. If you want at home, put it anywhere you want. And you will obtain exactly the same answer I obtained. I will obtain within 3 minutes. Okay, cool. Third question? No? Everything good? Okay, guys. So now let's focus on work of non-conservative forces. But before we focus on that work, let us show all the forces acting on the system. Okay? So let us draw FBD. FBD at arbitrary position. Okay? So, or actually, no, let's not draw FBD. I just would like to show only non-conservative forces acting on our system. Okay? Only non-conservative forces. Okay? So show only non-conservative. This is not FBD, yeah, because on FBD we show all the forces, yes? In here I will just show non-conservative forces. So I think that the non-conservative force is definitely normal force, right? And I think that we have one more, which is friction, TF. And we don't have any other. Obviously, mg acts on our system, yes? But mg is conservative force. I'm not going to show it here. Also, at some point, the force from the spring will start acting on our system, yes? But spring is also conservative. So I'm not going to show it on this drawing. Is this clear? Yeah. Okay, so we can write in here work of normal force plus work of friction. And I think that for the third time this semester, we are just going to say that this is 0. Yeah. N does not do any work. And I hope that most of you know why. Because this is our displacement vector. So this is our ds. Yeah, and you can clearly see that there is a right angle between n and ds, right? Our n is perpendicular to ds. That's why n is doing zero work. Okay, so let's focus on friction. So in here we will have u-12 of tf, and let's express it in even more mathematical way. So this will be an integral from the beginning till the end of tf times ds. Okay, so I can maybe move these forces here, and I will have more place in here to write. So I believe that our tf points in the opposite direction than ds, yes? So I can put in here integral from the beginning till the end minus tf ds. And by the way, our tf is mu k times n. So our tf will be mu k mg cosine theta. And we can all see that this is constant. Okay, so we have integral of minus mu k mg cosine theta ds, and maybe some of you would like to join the discussion. Yeah. Can any of you tell me what are the integration bounds I should put here? In other words, what distance is covered by our particle? Yeah. Anybody want to join the discussion? And I can scroll up the board. I know you know. Yeah. If you look at these two drawings, what distance is covered by the particle? Daniel. Awesome. Exactly. Thanks. Daniel is right. And I'm going to use what he said in here. So it goes from 0 to L plus S max. Exactly. And since our integrand is constant, we can just write that u12 is equal to minus mu k mg cosine theta, open the bracket and write in here L plus S max. Okay, guys, so what? 100% of the problem done. Yeah, the rest is mathematics. So I'm just going to take this expression. I'm just going to take this expression. I'm just going to plug these 5 expressions we just found into this formula. So I think that T1 was 0. If I remember correctly, V1 was mg L sine theta plus 1/2 k delta square minus the expression we just found, mu k mg cosine theta L plus S max, and this is equal to 0. Okay, this is too big. I must shrink it a little bit. Let's say to such size. And what was that? That was minus mg S max sine theta plus 1/2 k delta plus S max square. This is long expression. I told you last time. Yeah, that in this chapter we will end up with one equation, but pretty long. Yeah. Okay. And I think that this is actually one expression with one unknown, because I think that we know every single parameter besides one. We don't know S max. We don't know S max here. We don't know, it's also here, and it's also here. Okay, but again, this is one equation, one unknown. We know how to solve it, yeah? So, and this will be quadratic expression. Do you see that? So I actually simplified it at home yesterday. So this is what I obtained yesterday. If you want, you can simplify it today at home, and you should obtain something like that. 1/2 k S max square plus S max times k delta plus mg mu k cosine theta minus sine theta plus mgl mu k cosine theta minus sine theta. Okay, clearly a quadratic equation for S max. Okay, so now if you plug in values and if you grab your calculators, you will obtain such expression: 5 S max squared plus 7.514 S max minus 124.861 is equal to 0. And then again, grab your calculators and solve that quadratic equation. Here are our roots. So S max is either approximately 4.302 meters, or another root is S max approximately negative 5.805 meters. Naturally, one of them is physical, the other one is not physical. all of you see which one is physical and which one is not. This is not physical. What automatically makes the other solution the answer to our question. So this is the answer. S max is 4.302 meters. Oh wow, it's a long spring. pretty long spring, don't you think? Okay, guys, this is the end of the question. This is the end of the example, and now mic is yours. Any questions? Olivia, I'm sorry, I didn't hear everything you said. Could you please repeat the question? You can do that, yeah, because of this observation. Yes, so your question is, do you have to write integral explicitly, or can you just write this expression right away? Is this your question? Yeah. Yes. So basically, our body travels from here till here. Yes. Our body travels from here till here. Yes. That distance is L plus S max. Yes. And the friction force acting on the system is constant. Okay. If the friction force is, if the friction acting on the system is constant, then I have nothing against you writing this expression right away. But you must write this explicitly, that the force is constant. Okay? Yeah. Just keep in mind that if the force acting on the system is not constant, it's better to do integral. Okay? That was the question? Yeah. Okay. Yeah. Anybody else? So what do you want to do now? Example number 2? Yeah? Okay. Let's do it quickly and we can start our afternoon. So as usually, please read and understand the problem statement before we start our solution. Okay, so what do we have in here? This time we have 3 bodies, right? We have body A, body B, and body C. And these 3 bodies have, each of them has different mass, right? Moreover, we know that our system starts from rest. So you already know what is the kinetic energy at the beginning, right? It's gonna be 0. And also we have bodies connected with a rope. Yep, we have a pulley system in here, but it's not a fancy one. Yeah, basically each body, body A has 1 rope attached to itself, and body B has also a rope attached at 1 point. So that means that velocities of these bodies will be equal. Yes, do you see that? So basically velocity of A will be equal to velocity of B, and also velocity of C. What else do we know? We know geometry, as usually. And they ask us to find velocity at configuration C. Velocity of each of the bodies at configuration C. Okay, so probably some of you, and including me as well, so some of us would like to solve that problem writing down work energy expression, between these two configurations, A and C, right? Some of us would like to do that, yeah? However, that would be incorrect solution in that case, because something happens at configuration B. At configuration B, we are losing body C. Do you see? Body C will basically stop. Oops, sorry. Body C will okay. Body C will stop here. Will stay here for the rest of the motion. Yeah. So basically, what happens at configuration B, we have an external force acting on the system. Yeah. And that external force is doing some work on our system. Yes. And that means that we should split our problem into two. We should first look what happens between configuration A and B, but B right before the impact, and then we should look what happens between B and C. Okay, but in this case, in the second case, we will look at what happens at B right after the impact. Okay, so that's the plan for that's my strategy how to solve that problem. In case you have some questions, you can ask them later, let's say. Okay, so think about what I said right now, and if something is not clear, you can always ask me a question. Okay, so let's solve that problem. We're gonna start with motion between configuration A and B, but B right before the impact. Right before the impact. Okay, but the strategy is the same. I'm just going to write this expression, T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And we will find these five guys. T1, V1, T2, V2. And let's not forget about U12 non-conservative. Okay. So I think I want to go for the easiest of these five expressions. I'm going to go for T1. It's 0 because system starts from rest. So what happens at configuration B? What kinetic energy we have at configuration B? I think that each of our bodies has exactly the same velocity. Yeah, our three bodies has velocity v. So in here I have to write 1/2 MAV squared plus 1/2 MBV squared plus 1/2 MCV squared. Okay, 40% of the problem done. How about potential energies? V1 and V2. Question to you, do we have any springs in the system? There are no springs. So the only contributor to our potential energy will be gravity. So I just have to write here MAG times elevation plus MBG times some elevation plus MCG times some elevation. And if you guys would like to help me, if you would like to join the discussion, you can just tell me what these elevations are. But I will also just copy this expression and I will paste it here for configuration B, because the story here will be exactly the same. Okay, I know that this question is easy, but I don't know. Do you want to help me? Is there anybody who would like to fill out? Is there anybody who would like to fill out these three brackets? This one, this one, and this one? Maybe I can do that, and you can tell me what happens at V2. Okay, so I will fill out these three brackets, and you will fill out three other brackets. Okay, so what is elevation of point A? I think it's 1.6. 1.6, yes, because I am looking at this elevation. How about body B? Body B is at 0. Yep. Body B at configuration A is here. And when it comes to C, I think that the elevation of point C is 1.9. Yes, because our body C is here. Okay, so this will be 1.9. 60% of the problem done. Anybody would like to do another 20%? What shall I put in here? James.
For mass A, I said it's not one because the thickness of
Yeah.
MA is 0.3.
Okay.
And then for mass B, I said 2.9.
Yeah.
And then for mass B, I said 1.
Bravo. Okay, thank you so much. I know that it was easy question. Yeah, thank you for collaboration. Yeah. Okay, so thanks to James, we have 80% of the problem done, and now remaining 20%. So work of non-conservative forces. Okay, question to you: do we have friction in the system? No. Do we have applied force in the system? No. So basically, this will be zero. We have one non-conservative force acting in the system, but this is tension in the rope. Yes? Tension in the rope acts on this body and also acts on body A, right? But that tension will do zero work, yeah, because it's an internal force and the rope is inextensible. So that tension will do zero work. Also, we have a normal force between body A and C, right? So basically, body A is pushed by body C, and body C is pushed by body A. Do you see that? There is a normal force between them. But again, they do not move relatively to one another. So work of that force will be zero again. Okay, so this is zero. So we can write in here, no non-conservative forces acting on the system. Non-conservative forces acting on the system. Acting okay. We have some of them in the system. Yeah, they are internal forces, but they do zero job. Okay, guys, so that's it. So now the only thing we should do is to grab our calculators and to find values of these 5 parameters. So I did it yesterday. So my T1 is 0. That was easy. V1 is approximately 118.701 joules. T2 is exactly 6 times velocity squared. V2 is approximately 101.043 joules, and work of non-conservative forces is 0. Okay, so now let's plug these values into our original equation, and we will end up with following equation. We will have 118.701, and this is equal to 6v squared plus 101.043. One equation, one unknown. V is approximately 1.7155 meters per second. And this is our answer, part 1. Okay, I think this is a good time for questions. Yeah. Any questions? So part B is exactly the same, but so we're just going to do exactly the same steps, but between different points. Okay, so let's do part 2. Part 2. So now we will focus on motion between B and C. However, right now, when it comes to B, it will be right after the impact, okay? So it will be right after the hit, okay? So let's write down our expression. Actually, you know what? I want to copy that drawing. You know, it will help me running that discussion much smoother. So I will have that drawing here, and I will not have to scroll up and down the board all the time. Okay. So we have our drawing here. So since we are right after the heat, that means that our body C is gone, right? Body C is gone. Okay, it stays here for the entire motion. Okay, so let me write down our let's call it favorite expression, right? T1 plus V1 plus U12 non-conservative. Yeah, that was not funny joke. I know. I don't know. T2 plus V2, and we must find these 5 guys. T1, V1, T2, V2, U12 non-conservative. And right now, subscript 1 corresponds to configuration B, of course, and subscript 2 corresponds to configuration C, config C. Okay. And we have only 2 bodies in the system right now, body A and body B. So that means that our initial kinetic energy will be 1/2 ma v squared plus 1/2 mb v squared, where v is the value we found at the end of part 1. So our v is approximately 1.7155 meters per second. At the end, we will have 1/2 ma v final squared plus 1/2 mb v final squared. And how about potential energies? I should repeat the same step as the previous one, yeah? So I just in here have to do mag times elevation plus mbg times elevation. I can also copy this one and paste it 2 lines below. Okay, so what is the elevation of body A? I think it's 0.7, right? Because it's here. The elevation of body B is 0.9, so I can put 0.9 in here. And I think that at the end, our elevation of body B will be 1.6. 1.6, and elevation of body A will be 0. So we will have no contribution in here. Oh, have I forgot about specifying the datum? I think I forgot about specifying the datum. Okay, sorry for that. During the entire problem, the datum was obviously here. The datum was aligned with the ground. This is my datum. In part A as well, yeah. I'm sorry for that, yeah. But you figured that out, obviously, yes, yeah. Thank you for that. Okay, 80% of the problem done. Actually, 100% of the problem done, because work of non-conservative forces is 0 again, for the same reason as before. For the same reason as in part 1. Okay, guys, so dynamics is done. Yeah, we are done with dynamics. The rest is mathematics. Grab your calculators and obtain values of these 5 parameters. So in here we will have T1 approximately 13.243 joules. Our potential energy at the beginning will be approximately 71.613 joules. Kinetic energy at the end is exactly 4.5 V final squared, when it comes to V2, it is approximately 78.48 joules, and U12 is 0. U12 non-conservative is 0. Okay, plug these numbers and expression into our original equation, and you will end up with 13.243 plus 71.613, and this is equal to 4.5 V final squared plus 78.48. Again, we ended up with one equation and one unknown, where unknown is VF. So for the final time today, just grab your calculator and find that VF is approximately 1.190 meters per second. So this is the velocity body A will hit the ground, and this is our answer. Okay, that's that. This is all I prepared for today. Any questions? I don't see any, but I will hang out for 5 minutes in case you want to talk more about it. Thank you for today, and see you on Friday. Bye.